Hello everyone, thanks for joining me in this review. My name is Frank, and in this video I will review a desktop tutorial on hyperspectral core scanning that I've published on my website frankstutorials.nl. The tutorial is titled Hyperspectral Classification of a Porphyry Copper Pebble Using a Decision Tree. This tutorial follows up on the previous exercise, Spectral Mineralogy of Porphyry Copper Pebble. A review of that tutorial can also be found on this YouTube channel. In the previous exercise, we did an exploratory analysis of a hyperspectral image of the pebble, and we came up with a number of spectral end members. Now, in this review, I'll show how to create a mineral map using the spectral characteristics of the spectral end members that we found before, and by classifying a wavelength image using a decision tree. The decision tree classification is relatively simple. It applies expert knowledge about spectral minerals and uses the wavelength position of absorption features, which are representative of molecular bonds in the mineral crystal lattices, as you probably know. Okay, so let's get started. So what I would like to do first is show an overview of where we ended in the previous tutorial. This is a photo of the pebble. It's called a pebble because it came out of a ball mill and it was round, and that's why we called it a pebble. So it was a resistant piece of ore rock. Well, we investigated this pebble, and particularly we looked at spectra of point A, B, C and E, which are representative of 4 different spectral minerals, an illite, a muscovite, a kaolinite, and a tourmaline. Well, we created several products from a hyperspectral image of this pebble, and well, one nice result was the wavelength map that we created. I'll show you again what it looked like. Yeah, so this is what it looks like, and I have to also open the legend so that you know what the colors mean. Okay. Yeah, so once again, different colors mean different wavelength position of the deepest absorption feature in the wavelength range between 2100 nanometers and 2400 nanometers, which often contains diagnostic absorption features for a series of minerals. You can see that, well, you can see the porphyritic texture of this rock, but it's dissected by these fractures and vein fillings, which have cyan colors, which is because of well, wavelength position of muscovite at around 2203. And then we have yellowish and reddish colors, which are illite and kaolinite minerals, which have absorption features at slightly longer wavelength positions. Okay, so this is a wavelength map. It's just for visualization, but it's based on a wavelength image that I'll show right now. I can close the legends. Okay, I want to show it as in a single band. I want to stretch it because now we can't see much variation. Okay, let's do the stretch. Now let's just make an histogram equalization. That is better. And then we can show it in rainbow colors. We can show the variation in rainbow colors. Okay, so this is a wavelength image of in band 0, the deepest absorption feature, the wavelength position of the deepest absorption feature. Okay, so you can hover over it, and then you can see at the bottom of the window the wavelength position, which is about 2209 here, and here it's shorter at 2203. And there are other images in this other bands in this image. So the second band is this one, is the depth, the interpolated depth of the deepest feature. The next one is the interpolated minimum wavelength position of the second deepest feature, the depth of the second deepest feature, and the wavelength position of the third deepest feature, and the associated depth. Okay, so this is what we did last time, and what we now want to do, we want to make a mineral map out of this. So we want to classify the hyperspectral image in order to see which mineral occurs where. There are various methods of doing this. What we will use here is it's a decision tree. Yeah. So, but you can also use other methods like, for instance, a spectral angle mapper that matches end members to pixel spectra, or you can do a linear spectral unmixing, where each pixel is then unmixed into the various end members in order to get an optimum result. Those matching algorithms are also available in Hippie. But we are going to use a decision tree. Yes. Okay, so and the decision tree we will apply to the wavelength image, because we want to use a method that uses the position of absorption features, because they are very robust. They're always, I mean, they're related to, so the strength of molecular bonds, and they're commonly diagnostic for certain minerals. Yeah, and in contrast to, for instance, the shape of the hull, that is more influenced by other factors, and that is often, well, not always a very reliable way to information about minerals to classify an hyperspectral image into the respective minerals. Yeah, so we're looking here at the wavelength position of absorption features. Okay, so the first thing that I would like to do is show a histogram of the deepest absorption features. Yeah, so we make a histogram and it looks like this. You can see that there is, well, the majority of the pixels have a wavelength position between 2200 and 2210, more or less. And then there are a few here at 2245. Okay, well, that is typical for this rock. And also makes it a bit difficult because the majority of the minerals, they all have the deepest feature at more or less the same wavelength range. So let's have a look again at the spectral end members that we have identified last time, to see if this corresponds. Yeah, so, oh wait, okay, yep. I have to indicate the folder where you find the spectra. Okay, so they're here. So these are 4 end members that we try to classify here: A, B, C, and E: halite, muscovite, kaolinite, and tourmaline. Okay, if we show them all in one plot, they look like this. Okay, yeah, there is this little bit unusual shape, which is an artifact of the data acquisition. But let's ignore that. We're going to zoom in this wavelength range between approximately 2100 and 2400, because that is the wavelength range over which the wavelength image was calculated. And this is then what we see. This is not continuum removed. And you can see that especially the tourmaline, which is the spectrum here at the bottom, doesn't have deep absorption features. So in order to compare the 4 spectra better, we'll do a continuum removal. Yeah, so we remove the convex hull by division. We plot them again. And we'll zoom in to this wavelength range. Okay, like this. And then we get this. So for all 4 end members, we can see that the deepest absorption feature is here, located here, around 2200. Then tourmaline has another feature here at around 2248, if I recall correctly. So there is a table where in the previous exercise where you had to fill out all these wavelength positions. So you can go back to that table to check. And then it has tourmaline has a 3rd feature here. Okay, we don't want this. Good. So it has a 3rd feature at the 2360, more or less. Okay, then we have 2 almost similar minerals, illite and muscovite. The muscovite is green. It has an absorption feature slightly shorter wavelength positions than the illite here, and both have an absorption feature at the 2340, 45 more or less. And that's typical of illite muscovite. And then there's this red spectrum, which is kaolinite, and that has a typical feature here at the shorter wavelengths, 2165 more or less. Okay, now we're going to use all this information to distinguish the different minerals in this in the wavelength image. But the first thing we'll do now, okay, I'll make this, I'll minimize this and this. We'll first have another look at this histogram. So as we have seen, the majority of minerals has a feature here, which is consistent with what we see on the right in this reflectance spectra. And we can see that, well, this peak consists of 2 populations. There's one here with slightly longer wavelength positions and one here with slightly shorter wavelength positions. It's probably because of muscovite, and then we have here illite, kaolinite, and tourmaline. But then we have this feature here I already mentioned. And the only mineral that can cause this feature is tourmaline, when it has the feature at the longer wavelength as the deepest of the 3. So the first thing that we would like to do is to identify those in the image. Okay, well, the next step I cannot do in Hyperspectral Python. To create these decision trees, we use Envy because it has a very nice editor for making decision trees. I am a big fan of open source software, and that's why I often use Hyperspectral Python. But in this case, we have to use Envy, which is of course a very comprehensive and good package. But you have to pay for it, of course. Right. So we are going to use the wavelength image for the classification. So I'll open that file. The wavelength image is this one, WAV2. Well, the 2 stands for a 2nd generation of the wavelength mapper. It's a bit different than the 1st generation. Okay. And then I go to classification and I open the decision tree editor. I'm going to make a new decision tree. This is what it looks like. Okay, and then I say zoom in. Okay, so what this does is at each node you can enter a logical expression and a decision, and if the pixel then complies to that condition, then it will follow a yes, and if not, then it goes to the no field, and then you get 2 new classes. I'll show you how it works. The first thing that I'm going to do is check if the pixel has an absorption feature that's deeper than 5% reflectance. And the reason why I do that is because there's also noise in the image, and noise also produces short or shallow absorption features. So I first want to check that if I find a feature, if it's deeper than 5%, because then I consider it as a real absorption feature and not because of noise. I'm going to edit the properties. And the first thing, well, this is just the name to remember what this node represents. I say band 2 greater than 0.5. Okay, and then my expression will be band 2 is greater than 0.05. So what it does here, it says my band, which I call here band 2, I still have to assign it a name later on, or I have to link it to an actual band in an image, is greater than 0.05, it's for 5%. So band 2 will be here, the interpolated depth of the deepest feature, and should be deeper than 5%. And I click OK. And now it asks me to pair this this B2 variable to an input band. Okay, and then I link it to the interpolated depth. I say OK. Then I have to give this a name, this class, and I call it aspectral. So everything that falls into this class doesn't contain spectral mineralogies, spectral minerals, because there are no deep absorption features. Okay, that's that. Then the next thing is to execute this. So I'm going to execute this decision tree. I'll say, okay, I'll execute it to a memory, so I'm not going to write a new file. Okay, and then this is what I get. Yeah, so the majority of the image is white, so it means that, and that coincides exactly with the rock itself. So most of the pixels that are covering the rock, they have absorption features that are deeper than 5%. There are a few specks here, maybe because of chalcopyrite, I'm not 100% sure, that have a shallower absorption feature. And the background has shallower absorption features. Yeah, so the black pixels are mostly the background here. Okay, okay, so that's the first step. And then we said, all right, now we want to identify this group of pixels, because they are probably because of tourmaline, because it's the only mineral that can have a deepest absorption feature in that range of the 4 minerals that we're considering here, of course. So let's add children. Yeah, so we add another decision node, and what we say here, band 1, deepest absorption feature should be greater than, well, let's say, what did they say here, 2230. It's a bit arbitrary, but at least we want to have this cluster of pixels in one group. Yeah, so band 1 is greater than 2230. Okay, I say okay. Then band 1 we have to pair with interpolated minimum wavelength of the deepest feature. Yeah, that's this band. Okay. And then what we get out of that is tourmaline. Okay. Let's give it an, well, we can just give it a green color like that. I click OK. Yes, and the remainder, actually, all these pixels, they will end up in the red class. Okay, let's execute this one. Okay, then we get this. Yeah. Right, so we have about well, less than 1% pixels in the whole image, so including the background, which are now classified as tourmaline. Yeah, if we compare this with this result, yeah, we can see that there are mainly these dark patches here and then some here. Yeah, so we call that tourmaline here. Okay, and then we continue. So the next thing, if we look at these spectra, the next thing is to try to separate kaolinite. And kaolinite is not so difficult because it has this deepest feature. So what we'll say, if the second deepest feature is at wavelengths shorter than 2200, for instance, at shorter wavelength, then we call it kaolinite. Yeah, and because the deepest feature of kaolinite is here, and the second deepest feature is here. We can also illustrate that here. So I can show the wavelength position of the second deepest feature. And if I make a histogram of that one, then we get this. Yeah, what we see now is completely different. So there are not many pixels at 2200 that have the second deepest feature, but there's a group here which is a shorter wavelength, the wavelength of kaolinite. There's a group of second deepest features here, that is typically illite muscovite, this wavelength range. Maybe at the longer side, a little bit of some tourmaline still, because that also has a feature there at the 2360. And then we have these features at 2250, and that is that's this other feature here of tourmaline. That tourmaline is causing a bit of troubles here. But okay, let's add this now to the decision tree to separate kaolinite. So we'll see, we say band 3, that's the second deepest absorption feature, is greater than 2200. Band 3 greater than 2200. Okay, I say okay. Then we have to pair the third band. Well, that's this one. So it's the interpolated minimum wavelength of the second feature. One command, you can see this jagged appearance, that suggests that it's not interpolated. These are just the band. I'm not 100% sure. Well, that's something we have to check, because it looks like that the peaks now coincide exactly with the center wavelengths of each of the bands. And if it's interpolated, I would not expect this shape. But it doesn't really matter much for our result. Okay, yes, I have to add a name here. Kaolinite. Yes. Okay. And then what remains? Okay, there's also green. Okay, but we can leave that for the moment. Execute. Okay, then we get this. So what we have now, we have some tourmaline. We have kaolinite, yes. So we have some. There's not too much kaolinite. It's a almost 7% of the image, of the complete image, is assigned to kaolinite. And then we have many pixels which are either illite muscovite and some tourmaline still in there. So what we'll do now, we'll go to this first band in the wavelength image. And we know that the muscovite has a shorter wavelength than the kaolinite and the illite. And you can also see that here. So the green one has the shortest wavelength. So the interpolated minimum wavelength is slightly longer than 2200. And that, as I already explained, that coincides with this population. So we'll now classify muscovite by adding the following statement. Okay. In the decision tree, I have to add children here. What we'll say is band 1, and the deepest absorption feature is greater than 2106. B1 is greater than 2206. Okay, we can execute. No, we're not going to execute it yet, because we first want to assign colors to it and a name. So this is muscovite. We'll give that a blue color. Okay, and for now I'll just change the color to something different. Otherwise, it's a bit confusing. Magenta. Okay. Execute this. Okay, then we get this. And now we can nicely see where there is muscovite, and it's also consistent with what we observed before. So muscovite in blue, that's quite a substantial amount of muscovite in the image. So about 17% of the image is classified as muscovite. And then we still have this this magenta class, which contains both illite and some of the tourmaline. Now we're going to use the second deepest absorption feature again to separate between those two. Yeah, so we classify tourmaline here in two different branches of the decision tree, which is not a problem. So what we'll say now is that if band 3, so that the second deepest absorption feature is larger than 2250, or maybe make it 260, that's here, yeah, then we select this as the second deepest feature, yeah, and that is typical of illite. Yeah, so then and muscovite we have already identified, separated out. So we're looking at this absorption feature at 2350. Yes, and if it's not illite, then yeah, it will be this cluster of pixels, which is the second absorption feature here of tourmaline. Okay, so let me put that in the decision tree. So band 3 is greater than 2260. Band 3 greater than 2260. And then I say okay. So if it is larger than 2260, yeah, then we'll end up here, which is then illite. And we give that the color cyan. Okay. And if not, then it is again tourmaline. Yeah, so tourmaline is classified twice depending on the deepest absorption feature in its spectrum, and yeah, that can vary. Sometimes it's not always the same of the 3 absorption features of tourmaline that is the deepest. Okay, let's give it another shade of green. Okay, now we can execute this, and then we get this. Yeah, so this is our mineral map, classified mineral map. Yeah, so what we can see is that there is muscovite along these fractures and vein fillings, yeah, with abundant tourmaline as well. I think tourmaline is a little bit overestimated, yeah, because you can see it here. It is present here in the wall rock as well, maybe a little bit overestimated. So, but yeah, I can live with that. Yeah, then there's kaolinite. That's difficult to identify here in this pebble, but it's different from the overall cyan color that you find here, which is illite. And then we have some clear concentrations of tourmaline here, and here, yeah, which and here as well, which coincide with these clusters of pixels here, where there's tourmaline, but there's also chalcopyrite. Okay, we can save the tree. Can give it a name. So decision tree classification pebble 60. Okay, and so now we have saved this decision tree. The nice thing is that whenever we have rocks from in a similar type of geological environment with the same type of minerals, you can just run this decision tree and then you get a classification. Right. Make this also capital. Yeah, one observation in this image, you can see that there are some vertical stripes here. Yeah, here. That's noise. That's image noise. So you have to see through that. So that's an artifact. That's something you could try to get out by filtering. But how to do that, I'll explain in another tutorial, which is still to come. Yeah, once you have created this decision tree, you can apply it in a hyperspectral Python on the command line. Yeah, so in that way you can automate it in a script and using Hyperspectral Python. That's one thing. There are also ASCII editors available to create these decision trees, but then you have to type it all, only the syntax in an ASCII file, and it's not so easy to understand what you're doing then. So it's not with a graphical interface like this one in Envy. Okay, so if we go back to the instructions, there's also some question about, what's now the accuracy of this map. Can you comment on that, or what are factors that influence the accuracy? Yeah, that's of course a fair question, because once you make a classification like this, you want to know how accurate it is, and how do you know how accurate it is? Well, there are a few things that I can mention now. Where uncertainty can come from, because we have identified four different end members. So we only looked at those four in order to make the decision tree. Well, if we have missed any end members, yeah, then they will also not appear in this classification. Yeah, so that could be a source of inaccuracy, that yeah, we have missed end members. Of course, we know that there's quartz, and we know that there are feldspars, chalcopyrite. With those, we cannot really classify it easily in the shortwave infrared. But there may be spectral end members that we have missed. That's one. The second thing is that there's variation within minerals because of chemical composition differences, for instance. And so maybe there is a variation in the different halides or muscovites that we have missed, that we have not seen in the exploratory analysis that we have done before. So that could be a source of inaccuracy, and it's already clear from the absorption features of tourmaline. Yeah, the end member that we have extracted has the deepest feature at 2200 and something. Let me just check. At 2209, but we have seen that in the image there are also tourmalines that have the deepest absorption feature at 2360. Yeah, so the relative depth of absorption features within a mineral can also vary to some extent. So that can also influence your accuracy. Then the minerals may be mixed in 1 pixel. Yeah, so of course, well, the higher the spatial resolution, the better the chance that you're looking at pure spectra. But with this resolution at 0.2 millimeters, there's probably a significant amount of pixels that have mixtures in it. Well, we have not really dealt with mixtures, yeah, because if you get a mixture, you mix deepest absorption features, and then the mixtures may end up in one of the two classes that the mixture consists of. Yeah, so that's another source of inaccuracy. Okay, and of course there's instrument noise that may influence the result. Yeah, maybe you have to do some smoothing, or you have to remove some of the column striping that you can see here. Sometimes it's not possible. It all depends on the quality of the sensor and the calibration, of course. Okay, so I think then I've come to the end. I've come to the end of this this review. Yeah, I hope it was useful and that you learned from it. I hope you've done the tutorial yourself as well. That's the best way to learn this method. Yeah, so I thank you for watching, and I hope to see you again in another video. Bye.